just sent everybody an email just, outlining some of the things that I've been talking about and that we've been discussing, which I think are important for the course. So, does anyone have any? Does anyone who's looked at that already have any questions about the with the summary of the various questions we've been studying? Doesn't move. Normally where I talking where I stand, of course I shouldn't stand there. So this is to be raised 500 pounds, 300 pounds. Does everyone know what weight is in pounds? I think that some things, often things are measured in both. I think that sometimes price is given in kilograms because of for legal reasons, and then it's what you actually are getting is specified in pounds. Well, one of the main questions that I suggested we look at is Bradley diagrams in general, and in particular the Bradley diagram of the which is called Pascal's triangle. Well, and actually that's just the latest version of it. I mean, for hundreds of years, over the centuries before that, it appeared in other places. And seems to be quite basic. Of course, it's related to the binomial coefficient. So, well, so one question is to look at Bradley diagrams in general, and consider the question of what you have to do to make them into a category. And I guess they would be well, since they're not quite sets that with structure, and which is preserved by maps. I don't think you can really describe it as a concrete category. In any case, maps going from one to another are arrows from one Bradley diagram to another. They're really, you want to look at equivalence classes of sort of pre-arrow. So something that you would think of first is just a way of going from the rows of one diagram to the rows of another. In other words, so you have a Bradley diagram, then you have edges between the rows, and then if you have another Bradley diagram, you might think about having edges between the arrow is supposed to go from left to right, then you have some edges going from the points in the left-hand row to the points in the right-hand row. Okay, and then you might say that this should be commutative. And what does it mean? What's it going to mean that this is commutative? Already just for two-step Bradley diagrams, and the edges for one, and edges for the other, multiplicity. This is sometimes this can be thought of as a multiplicity matrix, right? And here you have a multiplicity matrix, and this one going from here to here, I guess. Well, each of these horizontal assembly of edges could be thought of as edges with multiplicity, could be thought of as a multiplicity matrix, right? Okay. So, sorry? I didn't hear that, I'm sorry. Well, multiplicity, yeah, I was talking about multiplicity. Well, no, come on, we've already interpreted the edges as corresponding to maps between matrix algebras. If you have a map between a matrix algebra, what's important is the multiplicity. In fact, that's one of we've been discussing the classification of AF algebras, and for finite dimensional algebras, for finite direct sums of matrix algebras, or even just for single matrix algebras, what's important for a map from one to the other is the multiplicity. And if it's a unital map, the multiplicity is determined, okay? It's like if you have 2 by 2 matrices and 4 by 4, then you could have a multiplicity 1 mapping from 2 by 2 into 4 by 4. You put it in the upper left-hand corner. You put 2 by 2 in the upper left-hand corner, and then put zeros everywhere else. That would have multiplicity 1. But multiplicity 2 would have 2 blocks, 2 identical blocks, 2 by 2 down the diagonal. And that would give you that would take the unit into the unit. But anyway, this is a very important exercise that maps between 2 matrix algebras are determined entirely by the multiplicity up to what you might call unitary equivalence or similarity composition with an inner automorphism. In the star algebra setting, unitaries, and the algebra setting of invertible elements. Okay, so that's but if you just abstractly look at the points labeling the direct summons and the finite dimensional algebra, then look at the multiplicities, record of the multiplicities between the points in successive rows. Then these are a bunch of natural numbers, 0, 1, 2, 3, and so on. There's no edge at all. That means the multiplicity is 0. So from here to here, there's no edge, so it's multiplicity 0. And that would be the 0 map, right? So it's pretty easy to see that 2 maps with multiplicity 0 are going to have to be similar, okay? Because you just prove that multiplicity 0 has to be the 0 map. But if it's multiplicity 1, you have two maps from say M2 into M4, and if the K0 map has multiplicity 1, the K0 map is a homomorphism from Z to Z, and so it's multiplying by some natural number, right? Well, if that's 1, then it's a fundamental. If you can prove this case, then you've got the general uniqueness theorem, which is important, which is crucial to classifying AF algebras. You prove that a map from M2 into M4 with multiplicity 1 has to be unique up to similarity, unique up to composition with an inner automorphism. What's an inner automorphism? Daniel, do you know what an inner automorphism of a group is? Say of a group. You know what an automorphism is? What's an example of an automorphism? Correct? Yeah, okay, and what's the next one? Well, if it's a abelian group, this one won't exist. But the non-abelian group, there are always what are called inner automorphisms. Well, what do you do? Boolean? Right? But that's what I'm asking what it is. Okay, good. Thank you. So what's an inner automorphism of a group, of a non-abelian group? They've written multiplicatively. Of course, no one's going to write a non-abelian group additively, right? Okay. How do you write it? What's an inner automorphism? That will be that'll be a left multiplication by a fixed group element. Well, no, that will be a set automorphism. It will be a permutation. It'll be an injective and surjective mapping from the set onto itself, but it will not preserve the group multiplication. It won't preserve the group operation. Okay. Anyone else want to? Yes, Jack. Sorry. All right. Well, that's to use a word like that, that implies that everyone should be giving the answer, right? Because everyone's seen the word conjugate, I guess. What are the conjugacy classes in the group? Well, it's two elements are conjugate. If there's a third element such that if you conjugate one of the elements by it, multiply it on the left by the element on the right, and on the right by the inverse, then you get the other element. That's what conjugacy means for elements. Well, now it's not so well known, perhaps, that the map from an element to a fixed conjugacy, a fixed element conjugate, the element and a conjugate to it in a fixed way. Okay? You have a fixed element. So we're talking about groups. It works exactly the same for algebras as invertible elements. But in a group, you map G into H, G, H inverse for a fixed H. H is fixed. Group is G. Okay. And then this preserves multiplication. Okay. So it's a bijective. Of course, it's a bijective map as far as the set goes. So it's an automorphism. Well, you have to check that theoretically, you have to, strictly speaking, you have to check that the inverse, the backwards map which exists is bijective. That also preserves multiplication. Okay, but it turns out that's automatic. It's for if any homomorphism between groups, if it's surjective, injective, and surjective, so the set theoretical inverse, then the set theoretical inverse also preserves the multiplication. That's a good exercise. Okay. So this is the automorphism of the group. It's written add G. Okay. It's an automorphism of the group. Capital A add G. Little a add is a notation for taking the commutator. This is the multiplicative. This is the multiplicative operation. But if you have an algebra and you have add x and apply this to y, then that's by definition xy minus yx. That's not a multiplicative, but it has a very important property with respect to multiplication. Because how many people know what have an algebra? We're talking about algebra. You map for fixed x, you map y into xy minus yx. That's a linear. It's obviously linear, right? It's a linear map. What properties does it have with respect to multiplication? How many people have run into that? Elon? It's okay. I think what you maybe just said was that it kills the identity of the algebra. If there's a multiplicative identity, a unit in the algebra, that's going to get killed. Okay, that's one thing that happens. But I'm not quite sure if that's what you said. But anyway, that's a special case. The proof of that is a special case of the general property. Okay, so this will come. We'll probably come across this. It's just a bit of a detour. But it's sort of a diverse. But you have the group then conjugating by element by any element, which is of course invertible. In a semigroup, if you have an invertible element, it would work too. And in an algebra, if you have an invertible element, it works too. It preserves addition and multiplication in the algebra. That's what's called the inner automorphism. And if all the inner automorphisms are trivial, that means at least all the central, all the invertible elements are in the center. And if it's a Banach algebra, this implies that it's a complex Banach algebra. And this implies that the algebra is commutative. There's an exercise. So I'm saying unique composition with an inner automorphism, which is of the form A goes to S inverse. Okay, where S is fixed invertible. Okay, so that's the so-called uniqueness theorem of the finite dimensional algebra, which is the crucial technical basis for the classification of the algebra. Okay, but does anyone have the my email in front of them? Do they want to remind me? Is anyone in a position to remind me what the first theme was that I in my outline? Oh yeah, Pascal's triangle. Okay, right. I didn't get as far as getting it on the board, but we're not quite finished with Bartley diagrams because what I was doing was emphasizing how important the multiplicity is for single matrix algebras or for finite direct sums. In that case, you talk about a multiplicity matrix, okay? And the point is, if you have two finite dimensional algebras, and well, just two rows, two Bartley diagram rows, and multiplicity matrices between them. If you want to erase the middle row, you can do that. Then you just multiply the multiplicity matrices, okay? That's in a deep sense, it's the same diagram, okay? Equivalent diagram in a deep sense. But that's what a map between two Bartley diagrams is. You look at just the same kind of multiplicity matrix between two rows at the same level from the different diagrams as between two rows in the same diagram. And then then you get four. If you consider just a two-step Bartley diagrams, then you have four multiplicity matrices. Okay, and then you want it to be commutative. Well, what does that mean, Abigail? What would saying you have this situation is commutative mean? Yeah, I think I know, I can tell what you're saying. I can almost I can almost see the words coming out of your mouth before they come out. Even I mean, how many people do? Chief Cam, do you see what commutativity means? Okay. Charlie, do you see what commutativity means? Well, it's a single diagram, and then it's sort of a special case of what you mean by commutative diagram in algebra, right? Except that these are not so much maps at the moment. If we put z's at the center of the points, we put z's, then they'd be maps, right? But before we can talk about purely combinatorially before we put in z's, and just say that when you go from one row combine, they're going between the two rows, with going to a third row, and the multiplicity matrices just multiply. And okay, but then going from here to here, this way or this way, the product should be equal, right? Okay, that's what it means. Now, in fact, Bartley didn't require that exactly. He said it should be true after you go farther. Okay, if we either you go this, these two combine roots, okay? But then you don't just stop here. You follow them both to the next stage or to some further stage, okay? So you say that it's commutative after some finite, after proceeding some finite number of steps, okay? And that's why it really becomes quite abstract. This is an equivalence class of arrows, if you like. So you have 3 arrows and then you have arrows. And furthermore, you don't have to map an arbitrary row to the corresponding row. You can just map an arbitrary, you can map a whole bunch of rows going out to, you can drop rows. You can drop rows and map a whole bunch of rows to certain rows farther and farther out on the right hand side. The levels don't have to correspond. So it's very vague, it's very loose what the Bradley diagram homomorphism is. Okay. And what's the reason for making it so loose? The reason is you want the category to be equivalent to the perfectly concrete category of ordered groups that arises. You look at the K0 groups of AF algebras, you get certain ordered groups, okay? And with additive maps, obviously what the map should be, additive maps, group maps, which take positive elements into positive elements or preserve greater than or equal to. That's the category of ordered groups, okay? So if you want the category of Bradley diagrams to be the same as the category of ordered groups, then that's what you do. You make it into an abstract category, and that's, by the way, you then, and that's what you want to do, by the way, to get a functor from AF algebras to Bradley diagrams. That's a functor. There's a functor, and that's something I didn't put it on my list of things to discuss, but it's a slightly subtle point that you have a functor going from AF algebras to Bradley diagrams, okay? And which is independent of even independent of how you well, let's not get into that right away. But so Bradley diagrams are very important. It was the first way of classifying AF algebras, and some people think it's the best way. It's so concrete, pictorial. It's pretty hard to draw an ordered group unless it's a subgroup of 2 squared. Okay. Plane. Well, Pascal's triangle is a very particular Bradley diagram. What is particularly interesting about it, besides that it's so simple, and it brings in the binomial coefficients. Well, it's an ordered group. If you take the diagram and instead of interpreting it purely combinatorial, you interpret it as a sequence of positive maps between ordered groups. Okay. But then it's you get a very simple ordered group. I mean, very interesting ordered group, and it turns out that it has a very concrete description in terms of polynomials with integral coefficients. Okay? And so that, of course, that's a group. Polynomials with integral coefficients are a group, and the deductive limit of each stage you have a group, and then you have projective maps, positive maps, so it's a deductive limit group. And it turns out that the inductive limit group as a group is isomorphic to polynomials in a natural way. If you say that the left hand oh, I don't know what's better, small x or big x. The left hand copy of Z is a power associated with the power of x. Then that gives you, then it tells you what all the other copies of Z should correspond to. Okay. If you say that Um, um, how do we, well, this this map takes one, by definition, one goes to one, and one goes to one. So the if we look at um, um, so the and now this one in the first row is doing double duty. Okay, it's the number one in the integers, but also it's the polynomial one, x to the 0. Okay, here we have x to the 1, and it's not doesn't belong to the group Z, but so the element 1 still belongs to the group Z, and you have the element 1 over here. So as a group map, you have one belonging to Z mapping into 1 plus 1, 1 comma 1. Okay, but if you want the association of these elements to polynomials to be a group to be additive, you want the association to be additive, then but if this is supposed to be associated to some polynomial, the second one in the second row, this is supposed to be associated to some polynomial. Well, then the sum of the two has to be equal to 1 as a polynomial. That tells you what it is, right? Daniel, what does it say, what does it say it should be? So this is 1, this is x. So what's this? So that this plus that equals that. 1 minus x, right? Yeah. Okay. But then at the next stage, how does it continue? So your next stage, you have x squared. So what are we going to have here? So there's a 1 and a 1 and 1. Well, I guess what you have here and what you have here is going to add up to x, right? So it's going to be x minus x squared, which is x times 1 minus x. And then x, what is it that if you add to x times 1 minus x, you get 1 minus x? Right? We don't have any negative powers. We're just talking about polynomials. Okay. But I mean, at some point we might want to do that. But not right away. Okay. But I would say that this is just requires a little arithmetic. So x 1 minus x plus p of x is supposed to be equal to 1 minus x. Okay. So p of x equals 1 minus x. Okay, well, times 1 and then minus x. Well, lo and behold, that's we can simplify it. It's the square of 1 minus x. Okay, so that's what we get. Was anyone about to say that? You were, okay. Were you maybe you were, okay, good. Okay, but that we want here is what we want here is 1 minus x squared. And it's interesting what we have, the successive monomials that we have are just the powers of, if you take 1 minus x plus x, okay? 1 minus x plus x, and you expand that to some power, and then you get powers of 1 minus x times powers of x. And the coefficients are, of course, the binomial coefficients. All right, but that's so this is clearly related to having the monomials here. Okay, I can't in a finite length of time I can't navigate the whole tight straight, the whole tight corridor, right? It's a very maybe I should be what did they do in the labyrinth? They one thing you could do is keep one hand on the wall. Okay. Another thing you could do is drop a trail of breadcrumbs behind you, but that might run into difficulty. Might be something that likes breadcrumbs. You could unravel. You could unroll a string. You could unroll a string. Okay, maybe that's what I should be doing. But anyway, this is now laying out what a possible isomorphism is between the group and the polynomial group. Okay, the Bradley diagram group and the polynomial group. Namely, at every stage, the generators could correspond to obvious monomials, x and 1 minus x. Okay, and you have to check that that's consistent. If you're going to map, in this row, you're going to map 1 to 1. In this row, you're going to map 1 to x, and this 1 to x, and this 1 to 1 minus x, and so on. If you're going to do that mapping, you want that to be compatible, right? You want that to actually make sense. So, for instance, but that's how we constructed it, okay? Because the only compatibilities we have to check are that since this plus this equals that, and at the z level, it should be true at the polynomial level too. But that's true by definition. Okay. So it's a group isomorphism. We have to check its surjective. That every polynomial, we have to check every polynomial. Well, we get these ones, right? We get the we have, in particular, we have the powers of x. But we're going to get all polynomials with integer coefficients. And so what? Well, that's already interesting. That you need to do this arithmetic to show that the map from polynomials to the group is surjective, right? You need to, because the group is generated by all these things. So every z has to come from some polynomial. And this is, but we've done enough work now to check. I mean, maybe you have to summarize. We've done enough work now to check that this is a group isomorphism. Okay? Anyone subject to a later verification? Does anyone want to question that at this stage? Okay, so I'll take that as approval. Okay, all right. This expression, I'll say that you're taking it under advisement. All right, but this is a very nice. Somehow it seems like a natural group isomorphism, and the Pascal diagram group. That group is an order group in a natural way, right? At every stage, you say that these ones and z's, the positive integers at every stage should be positive elements of the group. Okay, and in the limit is just the union, increasing union. These are inclusions. These are injective maps. And the order on the inductive limit group is just the positive cone is just the union of the positive cones, by definition. Okay, and that means that. So what we're saying, if it's to say this correspondence, this group correspondence is an order isomorphism, that says that with an arbitrary polynomial, it's positive in a certain sense. It's positive in a certain sense. It's positive according to the isomorphism. It's positive according to the group isomorphism. If it's a finite sum of monomials in x and 1 minus x, and adding up to for some finite stage, it should be a positive integral linear combination of 1 minus x to the n and 1 minus x to the n minus 1 times x, and so on. Okay? the monomials of the total degree n in 1 minus x and x. And so that's the order relation on the polynomials. It comes from the group isomorphism. And the question is, can we interpret this? Can we forget about Pascal's triangle and just look at the group of polynomials within their coefficients and say that this is a funny order relation coming from Pascal's triangle and the binomial coefficients and so on? That this funny order relation is a very natural one in terms of just evaluating the polynomials at certain points on the line. Okay. Well, in fact, that's what you can do. You can do that. And that's, as a consequence of that, you get the famous Hausdorff moment problem, just dropping out, falling out, okay? Spin off. You can prove there's the group isomorphism with a very natural order relation on the polynomials. Okay, well, in general, if you have functions on the line, on a subset of the line, positivity would normally mean pointwise positivity, right? I mean, that's a sort of a common idea that will give you an order relation. If you have functions on some subset of the line, then if you say one function is greater than or equal to the other with respect to this subset of the line, if the first function is greater than or equal to at every point, the second is greater than or equal to the second function. You have a choice. You could say greater than or equal, or you could say strictly greater than, or equal everywhere. If you want to have two different functions, you want to say that one of them is greater than the other. And well, the way what turns out to apply here is you look at a certain subset of the line, and you say that the first function should be strictly greater than the second at every point. And what's the subset? What's anyone want to hazard a guess? What Charlie? What's a nice good subset of the line for this order relation to sort of bring in? What's the simplest subset of the line? The simplest interesting subset of the line? Yes, and open or closed? Well, in fact, I want open, okay? Strictly greater than the first one. Well, if you want something to be positive and it's not identically zero, you want it to be strictly positive n on zero, then you just say you look at every point in the open interval 0, 1, and you say it should be strictly positive, okay? People say positive to mean strictly positive, that does cause confusion in mathematics often, even though some areas of mathematics do it. But in this course, I really would like to say strictly positive if that's what is meant. Okay, but that's the answer, okay? The polynomial is an integral coefficient, and you say the order relation is the open interval. That means that the endpoint is greater than or equal to, but you don't know whether it's strictly greater or not. But inside it should be strictly greater. Okay, that's the relation for, in the open interval. And so that's now an exercise, right? Prove that this order relation on polynomials with integral coefficients. If you never heard of Bradley diagrams or Pascal's triangle, then all you could say is this is a perfectly good order relation. Well, actually, there's another thing someone might want to tell you. This order group, Z of x, this order relation, it's an order group, and it has a property called the Riesz decomposition property, which is for an order group equivalent to the Riesz the Birkhoff-Riesz interpolation property, which says that which is very easy to say, you have any ordered set is a Birkhoff interpolation set. If, whenever you have a finite set of elements and another finite set of elements, and the upper one lies uniformly above the lower one. Okay? So every point upstairs is greater than or equal to every point downstairs. And the reason that's true is that there's some point halfway in between. Certainly if there were a point which is less than or equal to the upper one, or what I'm calling the upper one, and greater than or equal to the lower one, then every upper point is greater than every lower point, right? Greater than or equal to. So that, but that's the Reese interpolation property exactly gives you it. And well, this order group has that property, and if it comes from a if it comes from a Bradley diagram, that's obvious because the finite stage ones have that property, and so the limit will. It's easy to see that the property is preserved by taking a limit. Otherwise, could be a little tricky to prove, and it's important to prove if you want to get the Hausdorff from moment theorem, and then you want to know that this group is, if you take Q of X instead of Z of X, then it's dense in the polynomial. Sorry, dense in the algebra of continuous functions, dense in the linear space of continuous functions with respect to the sup norm on the closed interval. And that you can prove using, that's easy to prove using the Reese property. Of course, the Reese-Birkhoff property. But by the way, it's a well-known theorem. You could also just apply it. Also just appeal to it. What's the well-known theorem I'm thinking of? I think it's an undergraduate course. Okay, Rishi. Well, okay, but those people were separated by many years, right? Which one came first? What was Weierstrass's theorem? This is Weierstrass's. Yeah. Okay. So Stone he came along later and with a very nice generalization. Okay. And he did a lot of other things, not only mathematical theorems, but he's one of the people who put the University of Chicago on the map for mathematics. Well, I mean, more emphatically than it had been earlier. All right. So that's and it's a good. If you know all these facts that we've been discussing so far, it's interesting then to see how you get the Hausdorff moment problem. It just says that if you have a measure on the well, you notice first if you have a measure on the line on the interval 0, 1, then if you integrate the polynomial, if you integrate the monomial then you get something which is a well-known sequence of positive numbers. They're called the moments. Okay? And furthermore, these functions are decreasing on the interval 0, 1, just in the regular pointwise order, which you take into account when you're integrating. These functions get smaller and smaller, so the moments get smaller and smaller. And in fact, the differences between the moments are getting smaller and smaller too. Okay, so that's if you fill in this table with the moments, then you get positive numbers everywhere. And those are exactly the positive functionals on this order group. Okay. So the fact that the polynomials are ordered pointwise for integration, or with respect to fixed positivity in the interior of the interval, that's completely immaterial. That's right on. Okay, look. word partial to me doesn't exist. Okay, if you're going to if you want to have a total order, then say so. Otherwise, it's just an order. And when I was in first year, I learned what an order relation was. Okay, and nobody talks about a partial order relation. I don't think. Never heard of that. And you have pre-order groups, which are not quite the same as order groups. That's before you have anti-symmetry. And but no one ever talks about partially pre-order groups or pre-partially ordered groups, right? It's just a if that's what you're worried about, I think it's just a it's like obsession. It's a certain group of people to say partially ordered. But I know how it originated historically. Used to be the theory of ordered fields, maybe there still is, and that was meant that meant totally ordered fields. It didn't say so. So of course, after that, everyone has to say partially ordered. But now I don't think that happens quite so much. Does that answer your question? Okay, good. Sorry for the being so disrespectful. Okay, but but we have to check. So how do you prove Hausdorff? You have to know that positive functionals on the polynomials are the same as positive functionals on the continuous functions. Okay, but which are measured by Ries's representation theorem are measured. But we really want to know that every positive what do we want to know that the positive functionals on this order group are exactly coming from the measure, okay? Which means that they extend to polynomials. But another way to say that is the extreme. Look, if they form a simplex, it's easy to say they form a compact convex set, which is a simplex. And if you could show the extreme points are the unit interval, opposed unit interval, extreme points, extreme positive linear functionals are opposed unit interval, then we're in business. And but that now is a trick. The group Z and Z plus Z, Z plus Z plus Z. These are all rings. They're not just groups. They're rings. Multiplication. Z is a ring. You can multiply. And these embeddings are ring homomorphisms. Okay. So the inductive limit is not just a group; it's a ring. And by the way, look at polynomials. That's a ring too. And I guess you can see it's a ring isomorphism, not just a group isomorphism, what we're talking about. But the point is, and it's an ordered ring. The product of two positive elements is positive. Okay, take two positive in this sense. We're looking at, well, either sense. I mean, you look at either order relation, then it's the product of two positive elements is positive. Here it's kind of obvious. You're looking at positive integral combinations of these monomials. Well, any product of two of those will be another one at a later stage. So it's an ordered ring. Okay. Some people would say partially ordered ring, but I think we can just. My preference would be to dispense with that. But no one ever talks about totally ordered rings. And, all right. But there's a theorem. It says if you have a by the way, the ring homomorphisms from the ring into the real numbers are very easy to compute. Okay. Especially if they're positive. If they're positive, then they take ring positive functionals. At this stage, you'll have two numbers, lambda and one minus lambda. The value on this function will be lambda. Here it will be one minus lambda because they have to add up to one. because we're talking about functionals such as lambda 1 is equal to 1, okay? So, um, so the values are, at this stage, are numbers, real numbers, they're positive, and it's between 0 and 1. There's where the interval 0, 1 comes in. And if you just go to all later stages, you see the multiplicative positive linear functionals are exactly evaluating at points in the unit interval. So that's um, that's a computation of that's a computation of the positive linear function. So we're finished. We've got the Hausdorff moment problem. We don't even need to prove this is an order automorphism. It will be. We can prove it. I don't think we need it. Okay, you have to check that. Okay, saved by the bell. Point is that extreme points in positive linear functionals in an ordered ring, any ordered ring, are multiplicative. Okay, you have to prove that. That's easy, very easy. Extreme points are multiplicative. If it's multiplicative, then it's exactly evaluating at a point of 0, point of the interval 0,